I go by the name Faustina Petra Adabio from Ghana Communication Technology University, GCTU, and I'm a software engineer. Okay, so today we are going to learn about cache memory. What is a cache? A cache is a small and fast memory that stores frequently used data to speed up access, or in other words, is a high-speed SRAM between CPU and the main memory to store frequently accessed data. So what do we mean by SRAM? SRAM is a static random access memory and is a type of volatile memory that stores data using flip-flop. And then the CPU here is the central processing unit, the brain of a computer. And then is the primary component of a computer that executes instruction from software, example operating system, and then apps, and then games. I mean, you can name them. Okay, so coming to the structure here, this structure we see here is the hierarchy of cache memory levels. The hierarchy of cache memory levels. So let's start from the dual core or the quad core or the octa core. So here, this indicates a multi-core processor, and each core processes data independently. Okay, and then here MIMD means multiple instruction, multiple data, and is a processing architecture used in multi-core processors. Okay, so that's for the dual core or the quad core or the octa core, and then MIMD, multiple instruction, multiple data. And then let's come to the cache levels. So the cache level, we have level 1 cache, level 2 cache, level 3 cache, or the L1, L2, L3, how you choose to name it for your own understanding. So when it comes to the level 1 cache, here it's closest to each CPU core. Okay, level 1 cache is closest to CPU core, and it's very small but very fast, and then it each has its own level 1 cache. Okay, this is very small but very fast, and it's closest to the CPU core, and then each core has its own level 1 cache. And then moving on to the moving on to the level 2 cache. The level 2 cache is larger than the level 1, and is slightly slower than level 1. This is very small but very fast, and then this is larger than this level 1, and then it's also slightly slower, and usually still indicated to a single core. Okay, and it also acts as a backup to level 1. Here acts as a backup, it supports level 1. Okay, and then moving on to the level 3. The level 3 is the largest and then the slowest among the three. Among the three, level 1, level 2, level 3 is the largest and then the slowest among the three, and is shared by all cores. It's shared by all cores, and also helps coordinate and reduce access to main memory. It also helps coordinate and reduce to main memory. And then the arrows and then the flows here shows how data flows from the level 1 cache up through level 2 and then level 3 and then to the main memory. Okay, the arrows and then the flow shows how data flows from level 1 cache up through level 2, level 3 and then to the main memory. And then as the level number increases, size increases, and then the speed also decreases. Okay, as the level number increases, size increases, and then speed also decreases. As I said, this one is very small but very fast. That's the size. That's the size of the level 1. The size of the level 1 is very small, and then the speed is very fast as compared to the level 3. The level 2. The level 2 is larger than level 1. That's the size, and then the speed also decreases. So here it's very fast, and then here is slightly slower. Okay, and then here is the most largest and then the slowest among the three. So the size has increases to the largest, and then the also speed has also decreases to the slowest. Okay, so that's for the hierarchy of the cache, the hierarchy of the cache memory levels. So moving on to the next one, we have the cache basics. Okay, so the cache basics. Oh, sorry, we have the cache misses rather before we move on to the cache basis. So the cache misses here happens the cache misses here happens when the data a CPU needs is not found in the cache. It happens when the data a CPU needs is not found in the cache. So here are the three types of these cache misses. Okay, so when the data a CPU needs is not found in the cache, this is what happens. The first one is compulsory. So here we have the first access to data. So the compulsory happens the first time data is accessed. okay, the first access to data. And then it means it happens the first time, the very first time data is accessed. Okay, that's not yet in cache. And then the capacity, the capacity cache is too small to hold required data. So some data is missed. Okay, it's too small to hold all required data, and so some data is missed, as we have here cache too small to hold all needed data. And then we go to the next one, which is conflict. And then conflict also means also with the conflict, cache happens. Okay, with the conflict, cache happens. Cache has space. Cache has space, but mapping rules cause data to be replaced due to conflict. The cache has space, okay, but mapping rules cause data to be replaced due to conflict, as we have here, data evicted due to mapping conflict. And then we move on to the write policies. The write policies, this is so when we come to the write policies, this decides how data is written to cache and memory. Here, the write policies decides how data is written to cache and then memory. And then we have under it we have write rule. Write rule is um data is written with the write rule, data is written to both cache and main memory at the same time. So with the write rule, data is written to both cache and then main memory at the same time. So we have here write to cache and then memory simultaneously, slower but consistent. Okay, and then we move on to write back. Write back is when data is written only to the cache first. Okay, memory is updated later when the cache data is removed. And also it's faster but more complex. It's faster but more complex. Write to cache updates memory later when evicted, faster but complex, as I said earlier on. So hope that is clear. So we're moving on to the basic the cache basics. Yeah, so the cache basis. So the definition of cache, as I said earlier on, cache is a small and then fast memory that stores frequently accessed data to reduce access time to main memory. And then the key concepts, we have the cache hit. The cache hit. With the cache hit, the data is found in the cache, okay, and it's very fast. It's very fast. And then the cache miss also, that's for the cache hit. So the cache miss also, the data is not in the cache and must be fetched from slower main memory. Okay, example is the 100 nanoseconds, the cache memory. With the cache memory, the data is not in the cache and must be fetched from slower main memory. Example is the 100 nanoseconds. And we're moving on to the hit rate. The hit rate. The hit rate is how often data is found in the cache. Okay, higher is better, like 95%. Okay, 95%. And then the miss penalty, we move on to the miss penalty. The miss penalty here, the time lost when data is not in the cache and must be fetched from main memory. Okay, with the miss penalty, the time lost when data is not in the cache and must be fetched from the main memory. So as we have here, time to fetch data on a miss. Example, the DRAM and then access time. Okay, DRAM access time. And then so in short, cache speeds up your computer by quickly providing the data it uses most often. In short, cache speeds up your computer by quickly providing the data it uses most often. So we're moving on to the next one, which is cache organization. So the cache organization, each memory addresses map to one cache line using a formula. Index equals address, and then you bring the percentage and then the cache size. Okay, So indirect in okay, so let me have, so with the cache organization, cache mapped organization, which is the direct one. In a direct map cache, each memory address maps to exactly one cache line. There's no flexibility. Okay, there's no flexibility because in each direct map cache, each memory address maps to exactly one cache line. This is determined by a simple um, um, mathematical formula. Okay, which is this formula, the formula we have here. That's index equals address, then you bring the percentage sign, and then you bring your the cache, and then size, and then we move on to the cache line. So the cache line is fixed size chunks of data. Okay, fixed size chunks of data, and then block of data, example 64 bytes, transferred between cache and then transferred between cache and memory, leveraging special and then special locality. Then we move on to the tag. The tag identifies which memory block is stored. The cache identifies which memory block is stored, and then it's the upper bit of the address. It's the upper bit of the address, and then we also have the data block. Let me just add this to it. The data block. The data block is the actual data. Okay, it's the actual data. So when you are saying 64 bytes, that's the actual data. And then let me also add um valid bits. So the valid bits here indicates if the data is valid. That's to handle uninitialized cache lines. Okay, so that's all. And then also let me add this to the tag. The tag is a unique identifier for the memory block stored in a cache line. Okay, so I hope you understand and then you enjoyed the lesson. Okay, so see you in my next video. Remember to stop, not to stop learning, because if you stop learning you stop living. All right, so see you in my next video. Always learn, and then yeah, revise, and then you are good to go. So see you. Bye bye.